Hello, everyone. This is by Venice, coming to you for Anda Venice Hostel. Sorry. And tonight we have two talks focusing on different aspects of machine learning systems. But first, let's thanks the supporters of this edition, Anda Venice Hostel for hosting us, and Corley Cloud for the streaming. As usual, we'll start with the talks, each followed by a short discussion. After that, I'll share a few updates about our initiatives and upcoming events. And finally, we'll move on to some in-person networking. Starting now, for those staying for networking and who would like to eat something, with passing around the menu just to help the chicken prepare. You'll choose and confirm your order directly at the bar later. Okay. Let's give the floor to Árpád and Oliver with their talk on NLP, natural language processing solutions, and their optimization in a local environment. Give me a second.
Thank you. I will try to adjust the camera position so that we both can be seen.
Yeah. And I will make sure heard.
Yeah, exactly.
Being heard.
Yeah. So, good evening, everyone. My name is Khalid and Kocsis. We are from Solutions. We are a small AI company from Hungary. And tonight we are going to talk about some methods of using on-premise local natural language processing systems. So let's start with
our premise on this promise.
Yeah. Why isn't it?
Slide.
The slide works, doesn't skip the next one. This is ridiculous.
Yeah.
So a couple of one of the comments It should be all good now.
Hunky-dory now?
Yeah.
Okay,
Here.
cool.
Okay, so back to the beginnings. Yeah. So basically, a couple of weeks ago, our IT department sent us an email about a security breach with OpenAI, and basically, OpenAI started with a sort of apology, long paragraphs, lots of text, little information, basically bullshit. They said that nothing important was leaked, and of course that's not really true, because their third-party partner leaked persons' names and locations at the city granularity and the website that they came from. So basically, John Doe from Venice came from Pornhub.
It's nothing.
Yeah, it's really embarrassing, and yeah, but like, we are not trying to dunk on OpenAI. We are trying to dunk on every single company that's doing online LLMs, because what's the problem with this model? The problem is that this is not an isolated case. Basically, these big AI companies that provide services and chatbots and APIs and whatever, they are being hacked and breached all over the place. Like, there has been a study about just OpenAI, which has been breached more than 1,000 times, but we have no real reason to expect that the others are any better. So basically, there were studies about Claude, Perplexity, the creators of DeepSeek, you name it. Basically, there have been numerous security incidents, and and there is more and more and more, and yeah.
And actually, there ain't nothing new about this. It's just a random text box that you have an urge to fill in with random data on the internet. It's just that OpenAI and these all new actors and providers give you an even better or more of an urge to fill in with your company data. So it's always been the problem that on the web, you can just have a text box and have your secrets fed into some random company, which potentially can leak this information. Right. It's just that it tends to happen today more frequently, reason being that OpenAI, ChatGPT, and so on, whatever providers tend to give you better answers if you do. Right. And they give you this promise of taking care of your data, but this is just tends to be impossible.
Yeah, so basically, people have been doing this forever, but now they are doing it even more. And and so what's the response of like big companies? Like, if an intern copies the whole database schema into ChatGPT, like, Samsung's response is, we are big enough. We are going to build our own AI, and we are going to ensure that nobody else has access to our data. And that's fine. That's great. Except that you might, as a person or as a small company, have the same legitimate concern about your own data. Like, not many people are very conscious about their personal data, but I'm sure most of you are, because you are tech-savvy people. Most of the tech-savvy people and entrepreneurs still are. But if you are a small company like us, you just simply can't afford to build your own AI. Not ChatGPT, certainly.
So what do we do?
Yeah, so what do we do? And there is actually a really good solution.
We do our own solutions. We reuse open source software and host ourselves. That's what we do.
Yeah.
And this is just a small example on a small problem case, how well these AI solutions can fit into any kind of imaginary problems.
Right.
This being, and I give it back to you, Matthew, sorry.
Yeah, thank you. So basically, this is good old engineering. We try to build, we try to stand on the shoulders of giants, and we try to build like from Lego bricks from the existing solutions. And there are excellent open source models, small language models available, for example, which are good for small specific problems. So we brought to you a use case, which is a simplified example of a real problem and partnership that we encountered. So let's say we are investigating a criminal case. We will be talking about the famous Jack the Ripper case. You know Jack the Ripper, it's probably the most famous serial killer ever. Everyone knows about him. And the problem is that maybe in this criminal case, the evidence consists of many long text documents. And the task of a potential investigator or, say, police officer would be to discover the relationships between people and places and organizations in this criminal case. And normally, like the way a police investigator does this usually today is that they start reading the text from page 1 to page 600.
Yeah, there are expert users who can use the Control Command F, when you can text search stuff, but that's something that's innovative and not everyone can do that in the police force, let's imagine. Yeah. So what they would do is essentially just read through the whole damn thing, and it takes maybe weeks or maybe at least days, but maybe weeks. So why don't we use AI to solve this problem, right? It's a perfect example. You ask the AI, here is this wall of text. I want to discover the relationships between people and the most important locations. Okay, that's fine. But there are 3 problems at least. One problem being is that you obviously can't afford to paste all of this data into ChatGPT. It's too sensitive.
It's way too sensitive. It's way too much. And it's not going to be processed in reasonable time. Like if you have hundreds of pages of text, I'm sure all of you have at this point worked with some sort of large language model online.
Actually, can I have a question? How many of you have used a large language model locally on edge on your own computer or even mid-sized language model? Can you just raise hands if anyone tried at home? Olama or such tools?
Yeah.
2, 3 of you, 4, 5. So let's say like 30-40% of the audience have tried it.
Yeah.
With some extent.
Yeah, but online, basically, I assume everyone. And if you have used these things online, you can see that especially the new thinking models take sometimes minutes, like 2 or 3 minutes to come back with a response. That's obviously not going to work with a wall of text. And the last, and maybe the worst problem, put aside privacy and like speed, is that in a criminal investigation or in a healthcare, I don't know, medical investigation or whatever, you will want exact references to whatever the model says.
You don't reproducibility, so reproducible results.
Right.
So one query shall be at least comparable to the previous request.
And you don't want hallucinations.
And you don't want different hallucinations. You at least want consistent hallucinations, if anything.
Yeah, but in this case, I would argue that you don't want hallucinations at all.
Okay.
So the problem is that if you ask a large language model to refer back to the source where it got the quotes from, sometimes it will refer to completely non-existent parts of the text. We personally tried this with a completely different use case. It was about a service manual for a car. We tried to debug an annoying problem that nobody knew the solution for, and basically we asked ChatGPT to show us where it found the solution in the car's reference.
And it did. Funnily, it did, but it couldn't refer back to the exact page.
Yeah, basically.
So when I went back to the actual car mechanic to show him the proof that this is written here, I had to work 3 hours more to actually find the text in the damn document. And it was rightfully so, telling me that I'm referring to this document and this is actually what the manual said, but it couldn't tell me where it found it.
Right. So it was bullshitting about this very important part.
Yes.
And so what we are trying to do is we actually took some inspiration from a completely different kind of field of information technology, quantum computing, where there are these somewhat famous algorithms. I don't know if you guys have heard about Shor's algorithm. It's probably the single most famous algorithm. It doesn't matter what exactly it does, but the point is, it's there is this fancy quantum computing algorithm, but it's not just that. It requires some pretty extensive pre-processing and post-processing using good old classical computer science algorithms, because the quantum computer just can't process the information in the way that we want or can give it to. So our idea is similar with AI. you can see that we can basically just swap in the middle box instead of the quantum computing algorithm with the AI algorithm or machine learning model or whatever you have. The point is that you can use a small specialized AI model for solving a very specific and very well-defined task. And then use some classical pre-processing and post-processing to bring the data, the input, in a form that it can process, and to emit a data structure that you can then use for extracting structured information. And classical good old algorithms and heuristics are very, very useful for this purpose. So basically, we should be using a hybrid approach. And what we are doing in this case to solve this criminal investigation problem is we are basically like the machine learning core of our solution is a named entity recognition model. Like, if you don't know, named entity recognition is a problem or a way of using a language model to predict in a long text just the small parts, the small phrases or words that refer to specifically classified entities like persons or locations or whatever, like kinds of weapons, whatever you can think of. And basically a named entity recognition model just does that. It goes through the entire text and it tries to extract or mark the specific locations where these entities occur. And this is much better than trying to paste the whole thing in a very large language model and giving it a long-winded prompt and trying to convince it to extract all these entities and then refer back to them exactly in a long text and then just process the co-occurrences in some documents. A much better approach is to just make the AI do its job, very specific, very narrow domain, and we should tell it to just extract these entities. And then we use like classical graph theory, come up with some heuristic that we can use for deciding which locations and which persons are in a strong relationship with each other. And then we can use that to build a graph and then use classical graph theory and the graph algorithms and visualization tools to give a much better idea and give an exact result of what we want. So basically the long text that we presented in the previous slide is much better described by this this slide. So in come the documents, and then the only part that really requires AI is what is used as the input of the machine learning model. And then whatever comes out the model, it will be processed by, for example, building a co-occurrence matrix, like this person and this location occurred in this document or this context window at the same time. And then you can build a graph, and then you can extract useful information and actionable information from that insight, from the data structure.
Yeah, so this is just a simple enough pipeline that can be done on a machine, on an actual laptop computer today in a reasonable time. You don't need to burn the energy of the world in some random Arizona server park.
Right. Yeah, so actually, we would like to show a small demonstration of what this thing is capable of. I already have we realized this is a small server, client-server application. So I already have it running in the browser.
It's in Furrylang.
Yeah.
It's in Rust. Yes.
This is the place of advertisement here.
Yeah.
Yeah. So the point is, what you see here is we already preloaded the Wikipedia article from the Jack the Ripper case into the software. So it has ingested the text. And now we will be able to type in some kinds of entities that we would like to recognize. For example, I can type in person. I can add maybe like place or even better location. And then what will happen is if I press the analyze button and just look at look at how fast it is. Takes a couple of seconds.
How many kilobytes of data is this?
It's 45 kilobytes of data, but it's not actually processing all of it. That would take a bit longer, to be entirely honest. But like this is much faster than pasting it into a large language model. And what happens here is it built the network of locations. It built a network of persons, and then yeah. So just to explain the output a little bit better. So in this list that you see is every single occurrence of, for example, of locations in the text. They are grouped, so obviously a specific location like Whitechapel in England might occur in several different places in the original text. And the great thing about this model is that it can tell you the exact location where it came from. So this is by the mechanics of how it works. It can basically classify exact parts of the text, and it can tell you. And we are using this information. So if you click on this specific occurrence, it can refer to you back to the specific location where it came from.
Heuristically, so like this is actually replicatable.
Yeah. So it's not heuristic. It's completely algorithmic. This is completely exact. Yeah. And basically you can do this with anything. You can do this with of course the name of the criminal itself. It occurs several times. It occurs like I don't know 10 times in the text, obviously. And every time you click on one, you can see where it came from exactly. And then basically what you see here, this graph data structure, just shows how strong a connection there is. Yes, question. Yeah, sure. Yeah, like this. Is it better?
Can we pinch zoom? Yes, we can pinch zoom.
Yeah.
So, looks like. Yeah. So these are the people of interest in this criminal case.
Yeah,
we've got the victims, right? So these are really interesting examples of people that he found.
Right. So these are the victims, and you can see that the heuristic we are using is that people who occur in close vicinity to each other in the text, they are deemed to have a stronger connection. And you can see that the victims are really forming a cluster. So even this simple.
Sorry.
This isn't better.
No, this is right.
So even a simple heuristic and a simple algorithm and a simple use of such a model can result in very useful insights about the data. Like this was, I don't know, this demo took like 3 or 4 minutes, and this is already much more interesting and much more digestible than if you had to read the whole damn Wikipedia article, right? So yeah, question?
Very small one. What's the relation between the thickness of the lines and the numbers? Because they seem to be inversely correlated.
Excellent question. Yeah, the thickness of the lines is correlated with the strength of the connection.
Okay.
And the numbers are actually average distances in terms of characters between the entities.
Makes sense.
So the closer they are, the stronger the line. Yeah, the thicker the line. Right. That's a very important detail. Thank you.
Would you like to add another entity to look for? Do you guys have any ideas what to add? We've got now location and person.
Any ideas?
Weapon, maybe.
Person and how many times they were interrogated by the police as suspects? Something like that.
Yeah, frequency, maybe.
Frequency of detention or.
Okay. I don't think frequency occurs. Something related is maybe dates. Like we can add dates and times, and we can rerun the analysis. And yeah, it found some dates.
But this is interesting what you're saying now.
Yeah.
We need extra development. This is just a prototype to showcase in a fast pace. In a couple of days or weeks time, we can prototype such a product, and we can add other features to the pipeline, such features that can serve you well with the use case of that you just mentioned. So this is actually a good idea.
Yeah.
But this should come from the actual problem from the user who needs this force multiplier from the client actually. So we don't want to think out too deeply to what they would need. We need them to tell us what they need,
Right.
and that we just need to demo them what we can do, and we hope that this can showcase it.
Yeah, and this
Yes.
is kind of question.
Do you have a confidence threshold in order to understand which, let's say, part of the diagram is the model is really confident that it's true?
Yeah, sure. So just I will repeat the question so that the streaming will hear it as well. So the question was, do we have any sort of confidence metrics about the entities? And yes, actually, it's a very good question, because if you look at these numbers in the list of extracted and recognized entities, these are the probabilities that the model assigned to each entity. So basically, we have some threshold, which is currently set to a very low threshold. So it finds probably everything that is relevant at the cost of a few false positives, but it will find everything that is relevant. But you can see that there are very different thresholds. So there is an 8% confidence, but there is also like 18 or 43, or in the case of easier entities, is like 95% or 97% confidence. So yeah, this is very quantifiable and it's very, very valid. Yeah, and this is kind of the point. So in a real use case, we wouldn't come up with this sort of demo first. We would ask the people who need the help with the natural language processing problem. What problem do you have? What tools do you want to have? What you are trying to solve? What you are trying to do? And the point we are trying to make this with this whole presentation is that the technology, the tools are there. We just have to have the knowledge and the expertise to put them together in the appropriate way. And
not every problem needs to be overfitted and overkilled with generative AI solutions.
Exactly.
And with just put some money in and free tokens, and then it will be solved to some extent. But what extent is it reproducible? Is it actually solved? The questions that us programmers, we are responsible of answering. That is this actually a tool, or is it just a toy?
Right.
Is ChatGPT a good toy sometimes? Is it a real tool for many use cases? It seems like it is, but it's also very dangerous because of hallucination problems and security and so on and so on. So then what? Yeah.
So this is basically what I already said. The nice thing about AI is that it's not a replacement to the classical algorithms and computer science knowledge and tools. We believe it's complementary, and you still have to know your classical algorithms, your classical heuristics. And the important thing, as always, I'm actually a bioinformatics scientist by day job, and the one thing that I learned on my job is that you have to start with the domain first. Like, you start with the problem, you don't start with the solution. It's very tempting to start with a solution as a technologist, as a programmer.
That's called research.
Yeah.
That's
Yeah, but that's not
research can be fun.
Yeah,
it doesn't
but
necessarily bring you money.
Yeah.
Or income or value, or what is value even.
Yeah, and the other thing is, like, this third point that we didn't talk about yet is small models and locally running AI solutions are nice because you can experiment with them. Like, there is no way you can prove everything. Like, a lot of machine learning research is heavily mathematical, and that's the right thing, because you have to understand these models in order to make something useful with them. But there is no way you can prove absolutely everything about these models mathematically. You have to experiment at some point. When you are doing an engineering job, you have to be able to try out these models. You can just say, I proved theoretically that this model worked fine, and then you find out that it doesn't actually work, then that you are making a mess. You have to experiment and iterate, and for that you need fast feedback. So you need to be able to run your models and maybe even retrain your models quickly. And that's where small local models shine. Yeah, so these are main messages to you today and tonight rather.
Yeah.
And yeah, we hope we can help you eventually. And if you have any more questions, please feel free to ask. Thank you very much.
Any questions?
So just like I actually have like two questions. The second one, maybe we can actually chat about it later on. I mean, it's up to you. The first one is very easy, and it is how do you measure that it's actually performing good, this approach? Like the one in which you need to like actually model data as a graph.
Benchmarking.
Yeah, benchmarking. Yeah, that's correct. And the other one is, okay, so this, I mean, so the example that you made, of course, makes sense when you actually have something which can actually be modeled as a graph. So the question is, intended use in this case is finding relationship between things, which makes sense for lots of, like text kind of tasks. But like in the very classical approach in which I have unstructured data and I want to get the structured data from it. So for example, I'm thinking about what I'm supposed to do, in the next weeks, which is I have loads of mathematical reports. I cannot upload them or use any, like commercial API because of I'm not sure they're totally anonymized. And so the thing is, I need to still, extract structured data.
You want your unstructured data into structured data.
That's correct, because I already know what data I'm looking at inside this massive amount of data, and I know that they must stay on my laptop because of, like quality issues.
I can tell you now one solution.
Yeah.
Apple's foundation models can do that today. Apple's just released foundation models.
Like the local models.
Yes.
Yeah, okay.
Foundation models is the one that you can actually have structured data and you can query up and just parse up random data into a structured way of representation, and it's all on edge. It is bound to the platform, but it exists. So there must be other vendors working on the same problems.
To do that, right?
I'm sorry.
I'm still running LM1 from 2020, so I'm not sure.
That's fine. I think it's
Can it
supported.
still work on it? Does it support it? Because mine is really old, right? I mean, 2020.
Which one?
I'm
Is it
checking.
M1?
I have an M1.
M1 is supported.
Okay.
So if it's on an Apple architecture, not on the Intel ones,
Yeah, not sure. It's the first one.
it should work on Intel ones even. It's just a matter of speed, really,
Okay, fine.
because it's based on a Metal API, and there are 3 versions of Metal, maybe a 4th coming. It can do it fast on an M1, M2, M3, and on an M5 now, even faster. NVIDIA must be able to do the same thing. They must have a similar product with a different name. It's just that we have to have a focus. We have laptops, Apple laptops, and they perform really well with a little energy.
I love it. We just And no, thanks for that. I was actually looking for like a use case for local models.
If I were you, I would try foundation models. It's pretty new. It just came out like 2 months ago.
No, okay, that's pretty good. Yeah.
That's what we're planning to use.
Okay, I'm actually going to experiment. Maybe we can actually stay in touch and see how it goes. And the first one was like, how do you benchmark this in this case?
Right. So I'm going to ask another question in response to this question. Do you mean like accuracy, precision, like metrics, or runtime? Or
No, not like profiling, but part in terms of like accuracy and yeah.
Yeah. So like that's I think that's pretty easy because there are corpora on the in like open data sets.
Okay, so you have use the same approach of like a classical LLM basically.
Yeah, you can use that. Yeah. So you take the corpus that is labeled, and then if you have the ground truth, then you can run your algorithm and the whole pipeline. Basically, it's worth benchmarking the model separately, and also the model with the whole classical pre and post processing pipeline. You run either, and then you compare it to the ground truth. And if you have like I don't know, manually annotated or somehow annotated ground truth, then you can do that. Yeah. Okay. Thank you. Really good questions.
Any other questions?
Anyone?
I mean, I have another question.
I can give you a
No, it's fine, it's fine.
Sorry.
My question is more like the general vision you have for your company. Like, do you have, for example, for the AI piece of your code, do you have like a default AI structure or architecture that you would try to use with any problem? Or your idea is like, give me the problem and then we design from scratch, whichever is the best suited AI architecture, whichever is the best suited algorithm architecture. You have already kind of a baseline and then you adapt it for each problem.
You know, good artists copy, great artists steal.
Yeah, it's both actually. So
We take inspirations.
yeah, so what happens is sometimes you really discover a really good model for a specific problem, and then you want to reuse the hell out of it because you are glad you don't have to reinvent the wheel all the time. Actually, this demo is based on such a model. I found like a couple of years ago this model called Gleaner, which is a really excellent solution. It has implementations in many languages. It has a good API. It has different kinds of models, and it's multilingual. So it's not just English because you know, I'm Hungarian. I need sometimes to process Hungarian text. It's absolutely perfect. You know, it's not perfect, of course. It's statistics all the way through, but it's very, very good. And I really want to use this model for, you know, when I have a named entity recognition problem, I will first try this. But I have encountered several problems where the state-of-the-art models just didn't cut it. For example, you can read about this on our blog. We were tackling a sentiment analysis problem, and we tried to use classical like small language models based on neural networks for embedding, and they were way too slow. And then we found a very interesting framework for model distillation, and then we distilled our own models from some earlier publicly available models, and they performed really, really well, and they were like 2 or 3 orders of magnitude faster. So sometimes we roll our own, sometimes we reuse open source models, sometimes we do the combination of both. It depends on the use case, yeah.
Okay, but very impressive indeed, because you need a lot of knowledge of a lot of models.
Yes.
Also, a second small question is like, do you also have like an example or use case that you're already treating, which is not text, like for example, images, something completely different than text? Or so far you're just focused on text processing?
Well, the thing is that we're quite literal as humans, and I mean that literally. So it's and the way that we express our words on paper or on the internet is by text. So even if there is another input, it would be translated into text at one point for it to be comprehended by an AI. Because we don't work on images, we don't want to understand. So this scope of problem, to my understanding, requires text at one point.
Well, I mean, I think I understood the question. Specifically, we didn't bring a demo related to images, but I think like the point is there are, of course, methods and models for even multimodal, really excellent open source multimodal models, which can, for example, align the embeddings of the images to the embeddings of text, or the embeddings of images to the embeddings of spoken language. And they can be used in just the same way. As of now, due to limited resources in the company, we are primarily focusing on text.
It's quite limited, all right.
Yeah,
it's the two of us.
Yeah, it's the two of us. So, yeah, and we don't have like 48 hours in a day, but it's definitely on the radar. Yeah.
Yeah.
So not yet, but coming soon.
So sometimes we just spend 2 hours on deciding to what to spend the next 3 hours on.
Yeah.
But the focus is really, really hard to find and keep our focus on something.
Yeah, let's finish here because we will want to make room for our next presenter.
If you've got a question, an extra question, one more question, and then
one more question.
we already got the time to. Yeah.
Okay, I've been like allowed by Alessandro, so I can actually.
Yes.
Actually, the question was about like if you actually can go back to the solution, the architecture basically.
Yeah, sure. I hope so.
Oh, yeah, sorry.
That one, yeah.
This one.
I cannot see it. No, this is demo time. Okay, so it is, yeah, fine. So is there, I mean, I'm not sure what's, okay, thank you. Sorry.
Sorry,
yeah.
it's a bit small.
Okay, so is there any part of training in this? Like which part is?
No, here, no.
It's just like, okay.
This already assumes
This is the inference part, right?
yes, this is only the inference part. This is not. It assumes a pre-trained model for now. Yeah.
Okay, fine. So, okay, fine.
Yeah.
Okay, this can be trained again. This can
Yeah,
be
sure.
reinforcement learned
Well, I mean,
or
if it
trained.
works already, why doing that? I mean,
Yeah, exactly.
Well,
but-
defined works, right? So it's
No, I mean apparently it works quite well, but the point is we didn't like the demo and the use case didn't warrant it. But of course, because it's like the boundaries of training and inference are very clearly separated, there is nothing that prevents us from just plugging in a different model and maybe training our own, or maybe just fine tuning. But like for us as a small company with like limited compute resources, it's more realistic that we would find some more generic model and a small corpus, and then we would fine tune the last couple of layers.
and I also think that it's important that we state here that this is also a really good plus for an on-edge AI, for an on-premise AI, that XYZ client can own their data, and their data can be trained upon. Yes, and it wouldn't be mixed with other people's data. Yeah, it's like brewing your own beer, basically. You don't want others. Yeah.
I mean, again, so, okay, you would still need possibly, let's say that you actually have like a very specific custom whatever solution, you would maybe still need to train part of it, which I assume is the, like the recognition part, whatever.
Right.
And then like still the, deploying is gonna be on edge. So, I mean, that can be,
Exactly.
smaller, yeah.
Yeah.
I mean, what I found kind of like hard for now is like balancing the need for accuracy and the size of the model. I mean,
Yeah.
Right.
Yeah.
Yeah, these are the exact problems.
Yeah. But the beauty of an algorithmic pre and post processing step is that a lot of the tasks that would decrease your accuracy are now just simply not performed by the AI, and they are just exact. Yeah.
thanks a lot.
Thank you very much.
Thanks.
And let's give the stage to our next presenter. Thank you. Try to.
Okay. Oh, okay. So, thank you, Árpád and Oliver, and let's move on to Sara. We had a talk on classical neural networks and more recent architectures. And okay, yes.
It's okay? No, va il microfono. Mi senti? Okay. Hi everyone. I'm Sara Ferro, a postdoctoral researcher at the Center for Cultural Heritage Technologies. And here today we are talking about a classical, let's say, a classical problem that is about image segmentation. And that is about image segmentation, and we are going to use Python, PyTorch, and Hugging Face. Okay, so if you want other information about the center I'm working on, you can scan this code. So, image segmentation. Image segmentation is quite a broad topic, and now it's also quite investigated. And there is a semantic segmentation where you go to classify the pixels, each pixel in the image that is present about different classes. So in this case, you have semantic segmentation that there are several balloons but the balloons are classified like with the same label. So there is no difference between the different balloons. Then there is instance segmentation. Instance segmentation is different because the instances of the different classes is differentiating. So you have the balloons that are classified differently between each other. And finally, there is the panoptic segmentation that is, let's say, a combination of the two. Because we have also the segmentation of the different instances of, for example, of, in this case, the different people. And also you have the image segmentation, the semantic segmentation that in general is intended like giving a label to all the pixels that is on the image. The first one of the most used also now networks is UNet. UNet is this kind of deep neural network based on convolutional neural network, and it has this structure like a U. Indeed, you go from the original dimension of the image to the original dimension of the image, and you go down sampling and then up sampling. And there are also skipping connections that helps you moving the information in the deep networks, so to not lose information while having deeper networks. Here I reported some information about how to create an environment, a virtual environment. You know that when you create a project in Python, it's good to separate the different projects, the different environments of the projects. And so, because otherwise you can mess up the different environments. And I generally use Miniconda. That is a lighter version of Conda, and it's widely used. But there is also other types of virtual environment managers, like Poetry, that is generally used, but when you want to deploy a package. So it's better to be used when you deploy a package. Also, one of the main points I want to stress that when you do a project, it's good to have also the Python version you're using, not only the versions of packages, because otherwise there could be errors and it is not fully reproducible. So I suggest you using Conda for this, because the environment YAML also contains this information, or you have to put this information somewhere else. So, however, we are going to use Google Colab because we have free resources of GPUs for a bunch of time. And also, when you think on notebooks, you think, okay, it is a silo code and cannot import anything because I have to report all the code there. But it's not true, because you can do these two instructions in order to also map a folder with all the Python code that you want to import, like modules. Okay, here there is the, let's say, the information about the UNet, but recently the most used models are based on transformers, like I think the ones that our colleagues used, and they are state of the art in natural language processing. They were introduced indeed for translation, but it's the state of the art also for visual tasks, so vision transformers. We will use NVIDIA transformer given out by NVIDIA, that is MIT-B2, that is a segformer, that is a combination like segmentation with a transformer. So in general, in order to train a segmentation model, we need not only the original images, but also the masks. Masks are, let's say, representing the parts of the image that represent a class. And you cannot give an input directly JSONs, but you have to give PNGs, so masks with specific IDs for the different classes. We will use a custom dataset because you know that in a Hugging Face you can have several datasets that are already well structured, and you can directly import the datasets package, and you have the dataset already structured in a dataset class of PyTorch. And so we use a dataset class of PyTorch that takes in input at least two information, that is the image, so the list of images that are the original data, and then the list of labels that are the masks that are representing the different classes. Okay, now we go to Google Colab because it's more understandable. Okay. I've already opened. Okay, we start from the beginning. Here we are going to install all the packages we need. So datasets, transformers, evaluate, accelerate, also TQ. Okay, okay, I share again the screen because it's not visible. Okay, I share directly the tab. Okay, here we have the notebook. Okay, here with Colab you don't need to. A moment. Okay, don't know if it's too much. I think so. Like this. Okay. With Google Colab, you don't need to have an environment, a virtual environment, to define a virtual environment because you use a local environment in the remote machine of Google. So now we are going to install all the packages that are datasets, transformers, evaluate, accelerate, and TQDM. Transformers is the package of Hugging Face that is for getting models. So we will get this model of NVIDIA from Hugging Face through this package. Datasets is also a package of Hugging Face, evaluate also, and also accelerate to put the model into the GPUs. And then there is this package that is, let's say, to have the status of processing, and that many times is useful. Okay, you can install the dataset we are going to use, that is the Pascal Visual Object 2012. It's a dataset with, let's search it, but with common objects in context, but it's not, it's like Coco, but it's much less big. So, like this. Non si vede, ok. Okay, so I share again the screen. Ok. Sì.
Questo se possono venire a darci una mano.
Bene. Window. Screen. Okay. So Pascal VOC is, let's say, here there is a representation of Pascal VOC. You can have a segmentation of different things, so could be person, motorcycle, horse, or bird, or cats, and so on. So they are common objects in real life. Ok. Ha qualche problema StreamYard? Enter screen, questo, share. Non si vede niente. Ok. Perfetto. So, this is, let's say, a visualization. It's a visualization of this data set. So we have people, like here we have a motorcycle and a person. Here we have horses. Here we have birds and so on. So we have in total 21 classes. And we will see that the classes are these ones that we are going to see. So there is the classical background class that in general is not used for training. So everything that is background is not really given to the loss. So it's completely bypassed by the model. Then there is airplane, bicycle, bird, boat, etc. So we have a total of 21 classes, considering also the background. But in general, is also this take-home message is that segmentation models in general don't classify the background because it's not informative in the end. So, okay, you can install this data set by using also a library that is Dataset Tools, or you can download the data from the website. That is, so here and download in this website, you can download the data, so directly. you can download it, then unzip and put in your Google Drive. Now I have already connected the Google Drive to Google Colab, so you can have your Google Drive with all the things you need. So here we have the training data, the validation data. For now we are using only these 2 folders, and then other things that you need. So okay, here we are going to install other packages that are needed. Peel for visualization of images, NumPy, then Transformer, evaluate, we import all the packages that are needed. So let's run this. Okay, so here we have the dictionary of all the classes that we have seen. There is from the label to the ID. Here we were creating the segmentation classes. So if you go inside this database, for example, we go inside the training folder, there are 2 folders. Then we have created this other folder that is the segmentation class folder. But in the original dataset, there are in general annotations that are given like JSON files. And then the real, now it takes a bit, but okay. They are .jsons. These files were saved like this. So the name of the image with the extension and .json, but these are JSONs. If you open them, you see that they are JSONs. So you see that each, let's say each data, the annotation is a JSON. And this is a common case. Let's say you don't have directly the masks, but you have the JSONs. And here the creators saved directly the compressed bitmap of the masks. And you have also the class ID and also the class title. So what is this mask? Is a person. The next is an airplane. The next, etc. So you have to convert these JSONs to masks. So this data here, so this mapping are representing the indexes you are inputting to each pixel of your mask. So the background will be completely 0. The airplane will be with ones inside into the pixels. The bicycle 2, etc. So this is your mapping. So your masks will be PNG images with the different IDs like the values. Here is what is done this code. I already did this. So here there is the class ID. So you are telling, okay, let's put in the mask the specific class ID. Here I've cut, let's say, the quantity of training data and validation data, because otherwise it will take hours to train. So now we run this cell and try to close this. So I put 1,000 training data and 200 training validation data. And also here you can see how you can create a custom data set. So as we already said, you need images and masks in order to train a segmentation model. Here we're passing the image paths and the lab paths. We are sorting them, and also we pass the list of names. So for each row, you will have the image, the path to the image, the path to the mask, the path to the name of the image itself. And then there is this, you create then from the dictionary, you create a dataset class that is a Python class. And then you cast the columns. This means that each input path, it gets the image, and so it stores inside the dictionary the image itself. So you will have a dictionary of images data and label images, and then also the name in this case, because we return a dictionary of 3 elements: image, label, and name, and they are all converted to images. And then we create a dataset dict that will be used by the model. So now we run this. We're using this model that is a segformer, so a transformer released by NVIDIA, but there are many other kind of transformers or networks. So you can go in Hugging Face and search for image segmentation, and you can have several checkpoints. So we are using this. Let's download this. Then we can do other, let's say, augmentation. So here we are doing a color jitter. So we change the brightness, the contrast, the saturation, the hue. But you can perform that augmentation, the training set as you think it is useful for the model to see. So here we do the transformation for the training. So here we are applying this transformation to the images, no transformation for the labels because it doesn't have any sense. And then we return the inputs transformed. Instead, for the validation, you don't do any transformations because you have to do the transformations only for the training. Like the metric, in general, for segmentation is used the intersection over union, meaning that your metric is how much a predicted mask overlaps a real mask, a true ground truth. And that is the metric that in general is used for evaluation. And then this is done here. Okay, let's run this. Here we created the two dictionaries from the index to the label and from the label to the index. So we see how many labels we have. We have 20 labels. It's cut out the background because for us it's not a label. And you see that 0 is the aeroplane, 1 is bicycle, 2 is bird, etc. We pass the model to CUDA, so now we are using, because here in Google Colab you can decide the type of runtime. Okay, for now we have put T for GPU, is a kind of GPU. So we were able to pass the model to the GPU. And then here we can give the training arguments. With Hugging Face is very simple because there are these wrapping wrapper classes that makes everything. You have only to input the parameters. So where you want to save the models, the learning rate, the number of epochs, the batch size for the training, the batch size for the evaluation, how many models you want to save for each run, and etc., etc. And then also if you want to push the model to the hub, in general, if you want to keep your research and not vast dimension in Hugging Face, you don't want to push the model to the Hugging Face till it is not good enough. Here it's also implemented weight and biases, that is a visualizator of the curves, but now we decide, not to visualize through one weight and biases, but directly save. So this is running. And then here it's, we are waiting for one run in order to see the results. In the meantime that is running, I go back to the slides. Because I want to stress something that I told before. So before we see that we can create a custom dataset by using the dataset class of PyTorch and using a function that is from dict. And so in this way, you can pass the list of, let's say, a dictionary with the list of images and masks to the dataset class. Then you can create images in this dictionary through this function. And then you create a dataset dict that contains the training and validation. This is, let's say, something that I've already told you. So in general, the background index is the index 0. And then, some models have this possibility to tell, don't use the 0 class for the training. So there is this parameter to reduce labels that you can set to true in order to discard the 0 class to be used for the training. Okay, let's see what's going on here. Okay, it's running. Okay. But in the meantime that we are waiting, do you have any? Okay, here there is a result. Here we have the mean intersection over union that for the first run is only the 3%. And here you have the category per category intersection over union. So you have the 20 classes and each class has its own intersection over union. And then it's going on. So it's going on with the training. Let me see here. Okay, I've already saved a model. So here you see that the best models are saved. Here there was a checkpoint that before I saved it before because we cannot wait. We cannot wait 1 hour here. So I stop it. You see that it works. And then we want to see a prediction. So we used an already trained model that I saved, that is called the checkpoint in general. And then we see how it works. It's not the best because I reached 60% of intersection over union, but it's only to see how it goes. Okay, here it's. Okay, this is the train. We have to choose the class train in order to see the result. That is 18. Let's see. Okay, the model is not performing the best, but this is the prediction for the training, the train. But if we wait more, we will have better results. This is the ground truth, and this is the predicted mask. That is not the best. However, all the code will be available in the GitHub of PyData. And if you have any questions.
I have two questions. First one.
Yeah.
First one. Is it possible to have multi-label on the same pixel with this model?
No, with this model, no. But they are named, I think, multi-class. But there are models that can give, let's say, a probability vector with all the possible classes. Here you have the best class, and that's all.
Okay. The second question is, how do you deal with class imbalance? If you have many examples in one class, let's say.
Okay, there are in general you can use OR data augmentation, so you can improve the classes that are less represented in the dataset, or you can use losses like focal loss, that is let's say a classical loss for balancing this thing. So there are parameters that you can set in order to weight more, let's say, the error for the less represented class. Yeah, these are the two ways, but there is also dice loss. There are many losses, and they can be combined. Thank you. See?
Okay, so joining on to the previous question, I will imagine if the model itself doesn't support multi-class, then you can still, it's not a small resource, but you can still train many models, one for each class, for each dependency. Do you see any advantage for doing that?
In general, if there is, let's say, a correlation between the different classes, like it's more probable that I see a cat and a table together. If you train independently the models, you will lose this information. So it's robust only in the case you have the classes that are generally appearing in All right. Okay. So, thank you, Sara. And thank you, Árpád and Oliver. And it's better this. So now let's move on to group updates. And we have our sessionals page. So if you would like to submit your talk for one of our meetups, you can use the QR code or yes, the URL. And about upcoming events, we usually organize events in the event month, February, April, and here or by a new partner venues across the area. And in May, there is the largest conference in Italy, focused on Python, Rust, data, artificial intelligence, machine learning, and coding best practice. And in June, yes, and AI-Conf in Milan. It is more, AI-Conf is more focused on artificial intelligence as a whole covering ethics, business, and technologies. And if anyone would like to suggest topics or host an event, you can use this QR code. And yes, that's all. So thank you for being with us. Let's say goodbye to everyone joining us. Only everyone has online and move to some in-person networking and see you soon.